So the next thing we're going to talk about is some more language. So we've learned domain and range, which is describing the possible x values and y values for a graph. And now we're going to talk about whether a graph is a relation or a function. So a relation is one that we won't talk about as much, but everything's a relation. Everything that has an ordered pair is a relation. There has to be a correspondence between the domain and the range, such that each member of the domain corresponds to at least one member of the range. What that means is that every x value has to correspond to at least one y value. So this x value, this is mapping. We don't use this a lot, but most textbooks think this describes functions and relations really well, because you can see that this x value, hey, look, it has more than one arrow coming from it. And that's okay for a relation, because a relation just has to have a relationship between x values and y values. You can show this with ordered pairs, right? So you've got a set of ordered pairs. Every x value has at least one y value, and you can show it with a graph. I'm going to talk about this vertical line test in a bit. You can also describe a relationship or a relation with an equation. If I put in any x value, let's say I put in x is 9, I can solve for the y value. Now you'll notice that relations, things that are specifically relations, are a bit funky. In other words, when I put in the x value of 9, and I said, well, what y value makes this true? Well, what value squared gives me 9? Well, I know 3 does. 3 squared is 9. But what about negative 3? In fact, there are two values for y that will make this true. Positive 3 squared and negative 3 squared. In other words, this x value of 9 had a y value of 3 that made it true, and a y value of negative 3. This is great. It's a great relationship, but it's not a functional one, and we don't solve equations that do this very often, where you put in a value and you get more than one output. Instead, what this course will focus on is functions. A function is a correspondence between the domain and the range, such that each member of the domain corresponds to exactly one member of the range. In other words, when you look from a mapping perspective, every x value only has one arrow coming from it. Right? Every x value maps to exactly one y value. Every ordered pair has different x values that have their own y values. It can be the same y value, but the x values are distinctly different. Graphs, again, I'll talk about this in a second. Okay, but let's look at an equation of a function. When I put in an x value like, I don't know, 9 again, ooh, I picked a big number. Why did I do that? So if I put in a value like 9 again, I get 81 minus 3, which is 78. When I put in an x value of 9, I got only one y value. That's functional. That makes sense to me. So we're going to talk about what we can do with these in a sec, but I want to talk about how to look at a graph and determine whether it's a function or relation. There's something called the vertical line test. A vertical line test is that if something's a functional relationship, when you draw a vertical line anywhere through the graph, you only hit the graph once, because vertical lines are all equations x equals. So every x equals, so x equals -5, x equals 0, x equals 3, every x equals line can only have one point of the graph that it crosses through, because you can only have one corresponding y value. Versus something like this, if I say, hey, x equals -1, at x equals -1, y could be, I'm just estimating, but like 5 or -1 or -3, and that's not functional. Okay, so if your graph passes through, or if your vertical line passes through the graph more than once, it fails the vertical line test. So this is a relation. This is a function. So what's this guy? Hopefully you've thought about it. It already has the vertical line drawn for it, so you can see it passes through once, twice. It's not a function. This is a relation, and oftentimes textbooks will just say not a function, because we are concerned about whether things are functions or not. So if we wanted to practice this skill, we could go back to these graphs and say, hey, are these functions or not? So if you draw a vertical line through this graph, I only hit the graph once, so this is a function. This guy, same thing, even though there's arrows that keep going, I'm only passing through the graph once, it's a function. Same thing here, function. I hope you like my nice sound effects because I can't stop doing them. If you do this guy, again, the arrows keep going, but even though the arrows keep going, we're still only graphing or passing through the graph once, so this is a function. This guy, function, and this is the only one that should make you pause and be like, ooh, I don't know. This one has a round bracket on top of a square bracket. So if I were to draw a vertical line here, I pass through the graph twice. But since this is an open circle, this is a ghost point. It doesn't actually exist. It's just saying, hey, the graph starts here and then goes over, but it doesn't actually start here. It goes everything to the left of here. So there's not actually a graph here, but there is here. So this is actually a function. Okay, moving on. So now we're going to focus on functions because functions allow us to do funky things with equations. So regular notation for an equation is something like y equals x squared minus 9x minus 12. I could put in a value something like x equals 2 and I could put that in and solve for y. And I could tell you that therefore when x is negative 2, the value of y is 10. Great. Well, as is the motto of most of my things in math, is that mathematicians are lazy. They don't want to write all that. So they came up with function notation. They're like, hey, if this equation is a functional one, meaning when you put in an x value, we'll only get one output or one y value, we can use function notation. So all we do is we replace the y with an f of x, and that makes it function notation. Well, what's the point of that? Well, instead of me saying, find the value of y when x is negative 2, I can just write this. Find the value of your function at negative 2. This is not f times negative 2, and that's something that people always confuse, and then they start trying to divide by negative 2 in the end. I'm like, no, it's just function notation. This is the value of your function at negative 2. You put in x is negative 2, and you get 10. So I can answer with this statement. Instead of having to write this out in words, when x is negative 2, the value of y is 10, I could say the value of your function at negative 2 is 10. And so I'm reading this equation in words. So now I can use that to ask questions. I can say, hey, a function f is given by this equation. So this is the expression that defines the function. And I could say, find this. So what is this asking you to do? Well, it's asking you to find the value of your function when x is negative 7. So everywhere there's an x, I'm going to replace it with a negative 7. So I've just drawn brackets everywhere the x's are, and I'm going to put negative 7 in for x. And then I just simplify. So this is 2 times 49, which is 98. Starting to doubt myself. I've made some silly mistakes in videos. Then I'm going to add 7 and I'm going to add 3. So then 98 plus 7 plus 3 is 108. So that means the value of your function at negative 7 is 108, or you have an ordered pair, negative a 7, 108. And then we can ask you to do silly things, like we can say, hey, find the value of your function when x is 5a. Why? Well, there's purpose for this, but for right now, it's just a practice of substitution. So again, everywhere there's an x, you're going to replace it with a 5a. So I just wrote out my shell and put brackets for x's, and I'm going to put in 5a. And then I'm going to simplify. This is 2 times 5a all squared, so I'm going to square the 5 and square the a. So this is 2 times 25a squared. You could also think of that as 5a times 5a, right, instead of expanding the exponent through, minus 5a plus 3. And then to simplify, I get 50a squared minus 5a plus 3. So the value of your function at 5a is 50a squared minus 5a plus 3. Awesome. All right, one more. One more thing is that we can use a graph of functions to define function values. In other words, if I know that f of x is equal to x squared minus 5, I could give a graphical representation of the solutions to this equation, and this should have arrows on the ends of it. And if I said to you, what is the value of this function at 3? Now I have the equation. I could plug in 3 for x and get 9 minus 5 is 4. Or I could just look, because I have a graphical representation of it, I could say when x is 3, y is 4. And so the value of your function at 3 is 4. So then what's your value of your function at negative 2? Well, we look for where there's an x value of negative 2. And I say when x is negative 2, y is negative 1. So the value of your function at -2 is -1. All right, so pause the video and I want you to try these three. Find the value of your function at 0, 2, and -2. So hopefully you're coming back, and we said, okay, when the x value is 0, so when the x value is 0, we have a point here, 0, -1. So the value of your function at 0 is -1. What's the value of your function at 2? Well, we have a point here, 2, 3. So the value of my function at 2 is 3. And then over here, what's my value of my function at -2? At -2, again, I have a y value of 3. But even though I had the same y value, each x value only corresponded to one y value, right? If this was a relation, your graph would have a branch down here and you'd be like, oh no, well, that y could be this or this, which is why we're only dealing with functions. All right, go do your quick check and then we'll move on to the next video.